Okay, so this is what we figured out about light in the last episode. First, Grimaldi noticed that light can bend around things, and it was epic. Then Newton said that light was a corpuscle, which is basically a particle. Then, Young shined light down two holes and he got a funky pattern. Now this was important because this proved Newton wrong, and it was proof that light behaved as a wave. And then, Maxwell did a bunch of calculus magic and found out that light was made of electricity and magnets. And everyone was very pleased with that. And that's it. I don't know why it took me 9 minutes last time. I'd say that was a pretty good explanation. But if you would still like a bit more, then you can watch this. I honestly think you should be fine though, because that was great. Anyhow, I need to talk about my sponsor.
Hey Bodger, what are you doing?
Shut up, Greg!
This video is sponsored by My Free Time. But they don't really have a lot of resources at the moment with school and tests and all. So that is why my uploads are quite irregular. And that sure must be inconvenient for the good viewer that wants to stay updated on my uploads. Luckily, there is something you can do. Subscribe and hit that notification bell if you like the video to support my motivation and be able to stay updated.
Kinda looks like you're selling out a little bit!
It's none of your business, Greg!
Okay, the title of this video says that light gave us quantum mechanics. How did it do that? All of the theories so far were pretty classical, right? Well, after Young's and Maxwell's shenanigans, most people were pretty convinced that light was a wave. Everything seemed to line up in that direction. But there were a few things not right, and the simple nature of physical law as we knew it was about to end. Classical physics was about to go into shambles. Why? Well, quantum physics was about to be conceived.
And here we go. No!
Okay, that's a good time.
No!
Where are you going again?
No!
Alright, I'm rubbing my back on it.
Jack, stop. It's over. It's over.
No!
We're not doing this anymore.
What did you do?
I got angry.
No!
I'm
That's so sad. What does this sound like now?
It still works.
Okay.
It still got some kick in it.
Just because your child breaks its leg doesn't mean it's broken completely.
That's true. Doesn't mean you saw them off.
Around the end of the 19th century, there was something called the ultraviolet catastrophe, which, well, couldn't be good based on the name alone. The problem was that our model at the time that predicted the spectral radiance, which is basically how much an object is glowing in a certain wavelength region, and this predicted spectral radiance of black bodies didn't match experimental results. Black bodies are materials that emit radiation of all wavelengths. For example, the sun is a black body. It emits light of all wavelengths, but mostly visible light, which is why our eyes evolved to see light in the spectrum. Another example is the metal rod thingy in your oven that glows after it gets to a certain temperature. That's a black body as well. The key thing is that the black body spectrum does not depend on the material itself, but the temperature. So they all look like this, more or less, but the values are more or less extreme, I suppose, depending on the temperature of the object. Right, but why should I care about wavelengths or some objects? Right, who cares? Well, for one, scientists like to know about things, it's our thing. And two, we can tell a lot about objects based on their spectral composition. For example, what materials they're made of, as each element has a unique absorption spectrum. And since black bodies are supposed to emit all wavelengths, if there are gaps, we can figure out what elements those things are made of, like the sun. That's how helium was identified at first. We also figured out its temperature this way. So, you know, that's pretty cool. Alright, but what was wrong with our model at the time? What even was the model at the time? Around the beginning of the 20th century-ish, people were trying to find a maths model that would describe the spectral radiance of black bodies. And they kind of got it right, but not really. It was fine-ish, I guess, for larger wavelengths, but it predicted that radiance increases infinitely for lower wavelengths, which just doesn't happen. This is the Rayleigh-Jeans law that predicted this, and I've labeled it, but let's look at it in terms of frequency because that's easier to talk about. Here the equation implies that the spectral radiance is proportional to the square of the frequency, which is why it makes sense that the graph looks the way it does, the predicted graph, since it looks sort of like a quadratic, right? It also means that the radiance will tend to infinity as the frequency increases, so the wavelength decreases. But that's not the relationship that was observed, and everyone knew it was wrong. It's just, well, nobody had a better idea, so they just kind of stuck with it for a bit. That was until Max Planck came along and got the right answer using the wrong, I guess, method.
Now that I know you, now that you know me, till the end of time, we will always be special friends, special friends, special friends.
He derived the correct equation for the intensity of spectral distribution by making the assumption that electromagnetic radiation can only be emitted in small packets called quanta, because they're quantized, so there's only certain values that the energy of those packets can take. This is the equation that Einstein made for it, having photons have energy proportional to their frequency, with the Planck's constant being the constant. And Planck stuck that in there, fixing everything. This also explained a phenomenon called the photoelectric effect, which is actually what Einstein got his Nobel Prize for rather than his theories of relativity. I'll link a good video with a proper explanation and experiment, but basically what was found that if you shine a light onto a piece of metal that has a frequency above a certain threshold, electrons would come off. However, if you put on higher intensity light, that would cause more electrons to come off, but only if the frequency threshold is met. If the frequency isn't high enough, it doesn't matter how intense the light is that you shine on it, it just won't work. This makes sense if light is a bunch of little packets. The intensity dictates how many packets there are, and frequency determines the energy contents of those little packets. If the energy content in that single packet is high enough for the electron to escape the atom, because it can only absorb one packet at a time, then it does. The more energy content, the more kinetic energy the electron gains. So this quantum theory of light has experimental evidence. Okay, but if we're looking at light as a discrete, quantized packet of energy, we're basically looking at it as a particle, right? But we said that light is a wave, so which one is it then? Well, scientists at the time couldn't decide, so they called all the big brain people they knew to sit down and have a chat about it.
Yeah, this is big brain time.
And Niels Bohr proposed something quite controversial at the time, that our equations for waves say where you could find a particle of light, but it doesn't exist as a particle until you try to observe it. He also said this about electrons. By the way, when I say observed, I don't mean looked at by the human eye, and I mean it interacts with something like a measuring instrument or a photon. When we look at things, it's because photons of light bounce off those objects and come into our eyes. That's what I mean. Right, so Bohr's theory of light actually matches observations. It explains how we can measure electron and photon properties such as momentum, which is a property of particles, and we can actually measure the momentum of light, which is what Compton did. However, it also explains how Young could get an interference pattern with his double slit experiment, which implies that light has wave properties. It's because he didn't observe the photons, i.e. interact with them, before they hit the screen, so they could act as waves up until that point. This is the famous wave-particle duality which everyone talks about, which says that light can be both a wave and a particle, depending on whether you observe it or not. But Einstein didn't like this. He said that an electron is an electron no matter whether you look at it or not. He also didn't like the statistical uncertainty that came with quantum mechanics, and at one point he got really mad about something to do with God and dice. But anyway, the question is, why does light behave like this? Why do electrons behave like this? It was even found that even larger objects exhibit wave-particle duality to some degree, just on a much smaller scale. Well, it turns out that our separate models of particles and waves are not that separate at all, though they seem to be like this at the macroscopic scale. So what is it all then? If not a particle, or a wave, or somehow both? What is this both?
I don't know.